use our Pygmy meter readings that we've collected in the field to actually calculate flow of a water body. So what we've actually collected in the field are a number of velocity measurements, or in the case of the Pygmy, a number of rotations in a certain amount of time at locations across the creek, and we know the depth of those locations. So this illustration shows kind of this setup where we have all these stations where we're measuring velocity. In the field, what we tend to do is take one measurement of velocity 60% down in the depth profile. What you'll see in this sketch are that some of the readings, or some of the stations, have two readings. So one at 20% down and one at 80% down, or 20% from the surface, 20% from the bottom. Typically, that is the methodology for a deeper water. Equally, if it's deep enough to require two measurements, it's probably deeper than what we would safely wade into, and we would use a different method for measuring flow at that site. So we have these velocity measurements at each of these locations at 60% down from the surface. We also know the depth, and we know the location across our tape, right? So what we're essentially going to do is we're going to break up our stream into a series of rectangles. So I'm just outlining one of these, and you'll see them outlined in this illustration. So in each of these rectangles, we're going to calculate a flow. I have my newborn in the background, and so you will be able to hear her on this recording. Apologies, but that's what that background noise is. So for each of these rectangles, we will have a velocity. Now, one of the things that we need to know, there's a standard equation called the continuity equation that states that flow, which is usually represented as the letter Q, is equal to velocity times the cross-sectional area of that of the flow. So this is a key equation. So we'll use this continuity equation to take the velocity that we've measured at the center point of each of these small rectangles, and use our depth and our distance along the tape to give us an area of that cross-sectional area of that small rectangle. Essentially, those of you who have taken calculus, we're essentially performing an integral, where we're going to calculate a flow in each of these small rectangles and add them all up, and that will approximate the flow of the total water body. So one of the things that can be a little bit tricky is calculating this width of the rectangle, because our rectangle goes from halfway to the previous point to halfway to the next point. And so it's not necessarily just so our velocity has to be at the in the middle of that, not at one side of that. And so what we do is we know the location of our velocity measurement for that site and the next site and the previous site. And so to get a width that goes halfway to the previous site and then halfway to the next site, what we do is we take the distance along the tape for the next station minus the distance along the tape for the previous station and divide by 2. And that gives us the appropriate width. So we're going to look at a table of values and calculate a few of these to just demonstrate. So what we have here is the sort of data that you're going to come back from the field with. So a location along your tape. We will have to calculate the width column. We'll have to calculate the width column. We measured the depth in the field, and then we have a number of revolutions in a time. So we'll use that revolutions in time to calculate velocity. I'll show you how to do that on the next slide. But first, we're going to look at this width part. So this first station is our edge of water. So we don't actually calculate a width for this one because we have 0 depth 0 revolutions, which means we have 0 velocity and 0 flow. But what we do use this for is essentially to have the rectangle that represents our velocity measurement that was taken at this station at 3.1 feet. It will go halfway back to 2. So to get our width for this station, that's where our velocity is at 3.1 feet, what we would do is we would take 4.6 feet, which is the next station, minus 2 feet, divided by 2. So 4.6 minus 2 is 2.6, divided by 2 is 1.3. So our width for this one is 1.3 feet. So then to calculate a cross-sectional area for that rectangle, we would just multiply 1.3 times 0.55, and that would give us our cross-sectional area for that station. So we'll do one more of these. So if we're calculating the width for our station where the velocity is at 4.6 feet, we would take 6 feet minus 3.1 feet, which would give us 2.9 feet, and divide that by 2, which would give us 1.45 feet. So 1.45. So we would continue that down until we got to our other edge of water. So at this one where we have 9 feet, this is also 0 depth and 0 revolutions, and so we wouldn't calculate a width. So in this site, we would be using data from these middle 4 locations to calculate our total flow. Typically at a normal site, 4 would be not quite enough. We would want to do at least a few more, but this is just for demonstration purposes. So you would finish calculating out that whole width column, and then we would do width times depth equals area of each of those sub areas of our stream cross section. So as we illustrated on the previous slide, that width is the location of the next station minus the location of the previous station divided by 2. So it's half the distance between the stations that are on either side of the measurement that we're calculating. Our depth is just as measured on the waiting rod. Then our area will be that width times the depth. The velocity at that station is calculated using this equation. So it's 0.9604 times R. So R is the number of revolutions divided by the number of seconds that those revolutions happen. So as you saw in that previous chart, when we take notes in the field, one of the things that we write down are the number of revolutions and how long it took them. So that number of seconds is a minimum of 40 seconds, but could be more than that. And sometimes we have to use more seconds at very low flow when the Pygmy is spinning so slowly that we don't get a complete revolution at 40 seconds. But let's say, for example, that you had 10 revolutions in 40 seconds. R would be 0.25. So you would plug 0.25 into this equation to do 0.9604 times 0.25 plus 0.0312. And that would then give you the velocity in feet per second at that location. Our flow for that subsection of the creek would then be the area that we calculated times that velocity. And then our total flow for that location, for the location in the stream, would be the sum of all of the subflows, all of those integral flows added together. So the Pygmy comes with this standard rating table. The standard rating table, firstly, shows us that standard equation that we talked about in the previous slide at the top. So this is what we would use if we program a spreadsheet, for example, to calculate the flow. We would just plug that in. If you're doing it by hand, or if you need to spot check a spreadsheet or something like that, you can use the standard rating table to pick out velocities calculated for some standard times and revolutions. So across the top, these are numbers of revolutions. Down the side are the number of seconds. You can see that 40-second minimum. So for the example that I gave on the previous slide, for 10 revolutions in 40 seconds, the velocity would be 0.271 feet per second. And that's then what you would use to calculate the flow for that section. So you would do 0.271 times the cross-sectional area that was measured across. And so this is how we use what we measure in the field with a Pygmy meter. So our revolutions in an amount of time, our distance across our tape, our depth of our sight. This is how we use all of those things to calculate a flow rate for that stream location. Thank you very much.